It's time now to move on to the last presentation of the day, of the webinar, which is going to be by Steve Henley. So Steve Henley is a geologist with both public and private sector experience. He has been working for 10 years with geological surveys in Australia and the UK. And in 1981, he co-founded the Datamine Group, which is a market-leading international provider of geological modeling and mine planning software. Since 1993, he provides independent consultancy and contract research services. So he has been member of PERC also, setting standards for research and for standard research, sorry. And he's also very active in research. He's now participating in several EU projects developing robotics application for the mineral industry. And he's currently the president of the International Raw Material Observatory, the INTRO. And Steve will talk about the contribution of the ROBOMINERS technology to resuming operation in abandoned mines. Steve?
Okay, thank you, Claudio, for that introduction. Just a few more words of introduction. I'm a mathematical geologist representing the 4D Coders team. We're software geologists and engineers. Collectively, are mostly UK-based participants in the ROBOMINERS project. Now, I've pre-recorded my presentation to make sure I keep to time, as I've got a tendency to go off script when I'm doing live presentations. And I'll be summarising some of the work of the whole consortium, not just our own small part of it.
Good afternoon. Ava has introduced the ROBOMINERS project. What I plan to do in the next few minutes is to tell you a little more about the project and what we've done so far and what we plan to do. The project is a European Horizon 2020 project. It has partners from 11 European countries, and that covers a whole range of different types of organisation, from geoscientific SMEs, universities, governmental organisations, and non-governmental associations. The objective is to develop a bio-inspired modular robotic mining system, specifically for small and difficult to access deposits. This would be equipped with selective mining capabilities using a wide range of perception and mining tools, and should be capable of being delivered in modules to the deposit via a large diameter borehole if necessary, or if through an existing mine through shafts or adits that are already there. And it should be capable of mining not only underground, but also in either dry or flooded environments. Many of the targeted deposits will be abandoned mines in Europe, and ROBOMINERS will develop a solution for reopening many of these without the need for full recommissioning of the mine, and in particular without the need for dewatering the mine, because many will already have been flooded, maybe to surface. Many abandoned mines are old, sometimes very old. They extracted small ore deposits, and they were exploited in the past by manual methods. On the left is a copper mine that was mined in the 18th century. On the right is a lead zinc mine that was operated in the 1950s and only about half a kilometre from where I live. So many of these mines are flooded or otherwise unstable and unsafe for human access. This is an example of the challenges that we might find in flooded underground mines, where first of all we have the depth. This one is only 100 metres, but they could be many hundreds of metres deep. The timbers are ancient. In this case, we know that they're at least 160 years old, probably more than that. And the waste rock there is simply held up by the timbers, and we have no idea how safe it is. There are automated mines today, modern mines, but unfortunately mining equipment tends to be big and heavy and unsuitable for reopening old mines in small deposits. So mining machinery is big, whether it's for open pit mines or for underground mines. So what we need is equipment that is small for small deposits, and also that's remotely controlled or automated for safety, so that humans are not exposed to the risks of reopening ancient mines. Mining equipment suppliers are aware of the needs and have done a lot of work on designing new machinery, but unfortunately most of this is still too big for what we need. There are also a large number of research projects on such things as cutting methods and perception options. What we're looking for in ROBOMINERS is a new approach which takes inspiration from animals, burrowing and crawling animals, and also the mine designs taking inspiration from their feeding patterns. Locomotion of the robot is going to be one of the key factors that we need to incorporate. There are many conventional options like legs or wheels or tracks. Nature itself provides a lot of different possibilities, from swimming to walking and crawling. And we've analysed these to find out what the real options are for a robotic system. For example, one that we have looked at in detail is the Archimedes screw drive. This is not something that will be familiar to many people, but it allows vehicles to operate in a wide variety of different terrains, and it allows motion in any direction. Here we've set up a test bed to show how the Archimedes screw operates. It will work well in a wide variety of different materials, sand or gravel. Will also work very well in slurries. So this is a serious option that we should consider. But it's not the only option. Therefore, we've created virtual and physical models to test the different sorts of locomotion that are possible. The robot miner itself will be modular, with each module based on the same chassis, the same common functionality. The main modules will be production. This will actually break the ore, will do the mining. Then comminution, the crushing and grinding, followed by slurrification, which would take the comminuted ore and produce a slurry that can be transported to surface. Then a transport module, which actually contains the slurry pump. And finally, but not least, the control module, which contains the computer, the control unit, and data transfer capabilities. Many different sensors will be needed to sense the geology and the mining environment. Also to provide mapping and localization so the robot knows where it is, to assist in the excavation, and to sense the slurries that are produced. Geophysical and geochemical methods will be needed to assist in ore following, and this shows a couple of examples of the geophysical methods that we might be using. And we're developing instrumentation in the laboratory that we can test before integration with the robot miner itself. There are a very wide variety of conventional mining strategies that are used in existing mines. Some of these are suitable for robotic mining, but reopening old mines or even extending currently operating mines could allow us to use other mining strategies when extending into virgin ground to exploit new high-grade ore bodies, for example. And this is where bio-inspiration comes in again, looking at feeding patterns of worms and other creatures. These trace fossils on the left show feeding patterns of a particular ancient worm, and this leads to a couple of different mining strategy ideas for extracting the maximum of mineral with the least left behind in pillars. An important mine strategy that was developed fairly recently by the IPCON Institute in Moscow is the honeycomb mine, where the honeycomb is a load-bearing structure that's used in many composite materials, and its advantage is that it will leave the minimum necessary amount of ore in pillars and extract the maximum proportion possible. And finally, we need to look at the interaction between the robot design and the mine design. The robot design itself will have a number of constraints on the capabilities and hence on what mine design we can actually adopt. This example that I'm showing here is the turning radius of the robotic system, and that will control the design of mine layouts, how fast you can turn a corner. Well, this was a quick run through the project. I think I've kept to time, so we should have some time for questions if you have any.